Good morning, class. This is James Quinn, your instructor, and I'll be going over what's called the chi-square test for goodness of fit. And basically what this is a test, it's a hypothesis test when you're using qualitative data or discrete level data. We covered that in early chapters. This one's going to have a very similar distribution as the F distribution, but this one's going to be chi-square is equal to this distribution. Now, to find our degrees of freedom, what we're going to have to do is we're going to take the rows minus 1. So rows, degrees of freedom are going to be equal to rows minus 1 times columns. Oops, M-N-S, I think. Columns minus 1. So whatever that equals out to be. So if you have 3 rows and 2 columns, you'll have 2 degrees of freedom. If you have 2 rows and 2 columns, you'll have 1 degree of freedom. So I will go over that in just a few minutes. So you will have to find the degrees of freedom, and then you'll have to go back to your textbook to find the critical region or the critical value that will give you your critical region. And we'll go over that as well. So this test is not going to be any different than the tests that we have gone over so far, with the exception of the type of data that we're going to be using. So our test statistic is going to look like this: the sum of all our observed data minus our expected data. And then we're going to square that, and then we're going to divide that over the expected value. So that is our test statistic. So without further ado, we'll just go into this, and this will help you. I'm going to give you a question like this on your homework. So this will help you do that. I'm just going to have you do it by hand because you can do it in Excel, but it probably would take you less time to do it by hand, especially with the data sets that I'm going to give you, than it would by doing it in Excel. If you want to go into further statistics and things like that to analyze larger data sets, then your book has a chapter on how to do that in Excel. But just for this class purpose, we'll just do it by hand. So we're going to have, let's come up with a scenario. So my hypothesis, so I'm going to have the same thing. I'm going to have a null and I'm going to have an alternative hypothesis, and I'm going to say that observed values are going to equal expected values. Expected values. So this is going to say that observed values are not going to equal expected values. So basically, we're dealing with no negative numbers, so we're not going to have direction here. So I'm going to say that males are going to be more aggressive than females after playing violent video games. Let's just say that for just to give us some data. So I'm going to come up with a chi-square table. It's going to kind of look like this. It's going to kind of look like the F table, but it's not going to be as bad. So I'm going to have aggression and non-aggression. So I'm going to have males and females, and females. Now I'm going to have data. I'm going to have observed, what I actually observe after seeing people watching them play video games, and then their behavior after that. And then I'm going to have expected. So I'm going to have each one of these observed and expected. What would actually be expected? So observed and expected. Observed, expected. Now I need to fill in this with data. And what I have done is I have 100 people that I have observed. So I have 75 males that I observed and 25 females. So I observed males who were aggressive after watching video games or playing video games. I have observed 42 of those. And then I observed 18 females who were aggressive after playing the video games. Now on the non-aggressive side, I have 33 males that I have observed, and I observed 7 females. Now this would be pretty, this would be pretty common data since more males play violent video games than females, so I didn't get, as many females to observe as I did males. Now this is behavior right after the video game, like punching, their buddy or something like that, or cussing or something like that. So aggressive behavior. So now I'm going to add up my observed values, and 42 plus 18 is 60. I'm going to add up my non-aggressive, 33 plus 7 is 40. And I'm going to come over here and add up my rows. 42 plus 33 is 75. And 18 plus 7 is 25. So I've got those values now. Now I can go in and I can find my expected values for these numbers. So what I'm going to do here, I'm going to fill this expected value in of aggression for males, 75 males. So what I'm going to do, the total number of aggression is 60, so I'm going to take 75% of 60. So when I take 75% of 60, I get 45, and that's the expected value. Now, to get a percentage like that, I'll just put in, into any calculator, I'll just take 60 and multiply it by the decimal. So 60 times 0.75 will give me 45. Now I'm going to do the same thing for aggressive females. I'm going to take 25% of 60, which is going to give me a value of 15. Come over here to non-aggressive. I'm going to take 75% of 40, and that's going to give me a value of 30. And now I'm going to take 25% of 40, which is going to give me a value of 10. Now I have all of my data, so I can actually come over here and do my test statistic. So the test statistic tells me the observed minus the expected over the expected, and the observed minus the expected squared, of course. So let's go ahead and do that. So I've got 42 minus 45 squared over 45, my expected value, plus 33 minus 30 over 30, and I've got to square that, plus 18 minus 15 squared over 15, and then finally 7 minus 10 squared, that's a 10, over 10. So when I take 42 minus 45, I should get 9 over 45 plus 33 minus, I'm going to take 42 minus 45, which will give me 3, and then I square that, will give me 9. 33 minus 30 should give me a negative number 3. Squared will be 9 again over 30. 18 minus 15 will give me negative 3 squared, be 9 again. So 15, and then 17 minus 10, or 7 minus 10 will give me 3 squared, will be 9 again, over 10. So I'm going to add all these things up. So I'm going to take 9 over 45 will give me 0.2, plus 9 over 30 is 0.3, 9 over 15 is 0.6, and then last but not least is 9 over 10 is 0.9, and then when I add 0.2 up, 0.2 plus 0.3 plus 0.6 plus 0.9, I get a grand total, and this is my test statistic of 2. Now when I go into the back of my textbook, and let me do that real quick. This one will be on page 652 in the tables, and this will be, I'm sorry, 653, the chi-square distribution table. So remember what I said about my degrees of freedom. I have to find this in order to find the critical region. And so if I draw a little chi-square distribution over here, I'll know what my test statistic is for my critical cutoff. So when I come in and I find my rows minus 1 times my columns, I think that's right, minus 1, 1 minus 1, so I'm just going to get a 1, negative 1. So I got 1 degree of freedom. So when I come over to my table in the back of the book, 1 degree of freedom, I'm going to find with a alpha level, I can't forget that. My alpha level is my error rate, so I'm going to use 0.05. So 5 times, I could be wrong. There's a 5% chance here that I can make a type 1 error. I could be wrong, so I'm okay with 5%. So I've got 1 degree of freedom. And so I'll look into my book here. So 1 degree of freedom at an alpha level, you got the little alpha sign here, of 0.05 is a test statistic or a critical region of 3.841. So 3.841 is my critical region. So anything, any test, any chi-square, so chi-square is equal to 2 from this data with 1 degree of freedom. So I have a test statistic of 2, which does not fall into the critical region. So 2 didn't make it to 3.841, so I will go ahead and I will fail to reject the null hypothesis. I can't reject it. I can't draw an X through it. I basically have to say that there is no significant difference between the observed values and the expected values. So that is the chi-square, and that's how to do it.